Yes, full screen.
Full screen. And click OK. Good. For the eclipse.
It's great. It's amazing. We enjoy that. We enjoy that.
All of you, I think most of you were in the campus, right?
Yeah.
Ryan, you were also in the campus?
Yep. It's in the ground actually.
Was okay, you were with
Yeah.
Nahida.
We saw the inside of the ground.
I was outside of the stadium.
Outside of the stadium.
We saw.
In Nectar's lawn?
Walking.
Yeah, in between Neckers and Banking Center.
Okay. Good. Have you guys seen it before? Total eclipse? I think some of you said it has. So this is the first total.
I seen the one in 2017.
So partial on 2017.
Yes, that's what Lakshya also.
Partial last year, right?
Yeah, last
October.
year, where last year? Oh,
October.
but we didn't see it, right? Annular? That was the annular,
That's annual.
right? Or it was supposed to be an annular.
Oh, yeah, but then we would still see a partial here.
Yeah.
But it was cloudy that day.
I think we were not even in the partial range, right? Or were we? But it was completely cloudy, right? We had no chance.
Yeah,
But I
It's
think
not they went to Australia last year.
Yes, that's true, but that is not us. But then I was looking at one of the
I think
websites.
for seconds, we,
Yeah, I remember that.
yeah,
That always just came in.
yeah.
But we
I
didn't have
understand.
any glasses with us, so I don't think it was a partial for us.
Maybe
We
it
were
was
casting
for
it. We were casting an angular eclipse, but
so
I'm not sure if we had, because we didn't have glasses with us, right? If it was a partial, we would be prepared with glasses. Yes,
I know
but I do remember we were in the stadium and we
Yeah,
did,
but we had glasses.
we had glasses,
Yeah,
okay, so
We
maybe,
had glasses.
so,
But maybe it was cloudy, that's
Cloudy.
why.
okay. So the next one the department is arranging for is in Spain.
Spring, yeah.
It's going to be 7.5 minutes. Sounds good. 2026.
26. And total, it's total 1 month.
Yes, it's total eclipse and it comes from the northwest direction and goes to the south. South.
Yeah, that's, to mention Australia.
Yeah, this is pretty much Iceland, Greenland, Spain in that region. And in the website, it says the Greenland is supposed to have 29 minutes of eclipse, but that doesn't sound, I never heard of 29 minutes of eclipse. And in places like Greenland, sometimes the day length is only 29 minutes. I don't know that, but in the website, it does say that. So I feel
No,
it
it's
might
fine
be,
because it's on the.
it might be a typo
Oh,
too, it might be 2.9 and it became 29, so.
Maybe. If that one is 29, they have the 48 hours.
Okay. So we'll just get back on our course, please. Yeah, we had an exam on Thursday, correct? So, and I think I returned back the exams, yeah, and I haven't curved it yet. I was thinking I will curve it. Right, so I have to curve the exams and put a line for A and B somewhere. So I'll do that and yeah, only comment I have is Yeah, mostly it was okay. You could have done better, but that's a standard statement you make. But what I would say is that don't give up. Like that is A and B lines are not at all set. I know that last semester, I eventually decided that everyone should get an A. So that is a big factor of how much effort you put in this course with the final grades too. So, I mean, relatively speaking, all of you will be in that same order. But if I feel that most of you put in a lot of effort and the marks or the points you're getting is not a good representation, then I give it to everyone, sense. So don't give up, but at the same time, at this point, that I will draw an A and B line, and you will see that. So keep working hard, that's my only comment. And I haven't posted the new homework yet. We'll study Poisson bracket today. And it will be due on today's 9th, so +7 + 16. Stay this home. 9. That is the homework 9 going on, right?
Yeah.
And you have only a final exam afterwards. I don't have that. Have it written down. Do you know the dates? May. Day? That's Thursday?
Thursday.
9?
Time around 2:45 to 3:45. Around 2:45, I guess.
Okay. Check. With sister. Whatever I don't want to do, I put it in place. Okay. We want to switch gears a bit. We have done Lagrangian and Hamiltonian mechanics at this point. One of the important problems in history, in a sense, is the moment Newton's laws came up, it was used to explain the planetary motion. That was a very big success, and most of what we do in physics, if not engineering, is understand planetary motion and understand atomic motion of electrons and protons. That's a primary big time we spend in understanding, if you say, description of motion. Both of them are 1/r² potentials. One is gravitational, m1, m2 over r², gravitational force, and the other one is electrostatic force. Nevertheless, both 1/r². So we would like to study that. But before that, so let's say one lecture, or maybe if necessary, I will use the lecture of Thursday also. There's also an important feature where there's a connection between classical mechanics and quantum mechanics comes up. Again, planetary motion is mostly classical physics. And at this stage, you know the language of what we mean by classical physics is when Newtonian equations of motion are governing the motion of objects, that we say it's classical physics. And in atomic physics, apparently we need quantum mechanics. It's not exactly quantum Newtonian physics. You have to change things a bit. And often there is a distinct change in the way we address the problems, way we understand the equations of motion. But what we're going to do today is the closest we can get between the two. It's called the Poisson bracket. And what we have in quantum mechanics is a commutation bracket. And this Poisson bracket is what switches over to commutation relations in quantum mechanics. So that's and we will you will see that in your homework also, how you can jump from Poisson bracket to commutation our relations just by introducing the H bar and changing some definitions, so that will be useful. And here, let me motivate what Poisson bracket is. And if necessary, I will do more on it on Thursday, otherwise and I'll decide how much time is left and so. Okay, so, so this is broadly called Poisson bracket. But let's go back and try to understand, or try to sort of recollect what we have in our hands. Is this some in a way of summarizing our ideas? Let's go back and think in terms of Hamiltonian. So let's say let's start with Lagrangian. Lagrangian is sort of review. So we have like an action which depends on the position of an object, and it also depends on the initial and final position, and it is an integral of what we say is the Lagrangian, r by dt, and depends on the time. R is the position of the object. It has time dependence in it. I'm not shown it because that's implicit time dependence, and these are the two explicit time dependence. So T1 and T2 are the endpoints. At time T1, it has a position at T1, and at time T2, it has a position at T2. This gives you the Euler-Lagrange equations. So we say that stationary action principle states that this action should be an extremum, it could be a minimum or a maximum, locally minimum or a maximum. It need not be the maximum value. If you change it around a little bit, it is a minimum or a maximum. And this is written as pretty much rate of change of momentum is equal to the partial derivative of the Lagrangian with respect to the position. Here, P is the canonical momentum, and that's with respect to velocity, where velocity is a short form of derivative. Right. That's Lagrange, the formalism in terms of Lagrangian, but we liked the Hamiltonian formalism too. Again, you write the action, but this time as a function of position and momentum. So we give equal weightage to position and momentum. T1, T2 action as a number remains the same. If you were to evaluate this integral, it's an actual number that remains the same, and the definition of L is in terms of, it's written in terms of Hamiltonian. So let me take this V. So this is V dotted with T minus the Hamiltonian, which is R, P, and T. So it's basically, this is a definition of the Lagrangian is V dot P minus H. And instead of Euler-Lagrange equations, we now say it's a Hamilton equations. And that is R by dt is H by dP, and P by dt is equal to minus negative gradient of the Hamiltonian with respect to this is the analog of Newton's laws of motion. Like if you want to do any problem where the Hamiltonian is known, then And these are your equations of motion, and whatever those equations of motion tell you, that's what the motion is about. If that is the case, so notice this is the important piece here. So let's start, keep this in mind, and let's construct any function. Okay, right there. Think of any arbitrary function. And in general, it depends on the position. It can depend on momentum and time, right? In general, we can have many like position, momentum, angular momentum, Hamiltonian, that's a boost operator. So we had many such operators when we were listing out the operations that generate transformations, but let's stick to position and momentum because Hamiltonian gives some significance to that. And then ask, what is the Taylor expansion for this? So, or let's ask, given, let's say given, this is given to you. And let's ask, what is the time derivative of this operator or of this function? Like this could be something like a Hamiltonian, right? Hamiltonian is Rp and T. Think of any other function which has a position, time, and position, momentum, and time in it. We are saying it's a scalar quantity. It could be a vector also. This could be an angular momentum. In that case, this becomes a vector. And the time derivative of that usually is what motion is all about. Like most of the systems have an angular momentum, have a position, have a momentum, and we are asking, how does angular momentum change with time? How does linear momentum change with time? How does a spin change with time? How does a mass change with time? So these are the quantities we are interested in, like that's dynamics. When we say something is changing with time, we are asking what is the dynamics of it. And immediately you say that, okay, I know Taylor expansion, whatever is the dynamics, this should describe the time dependence of R, P, and T. So all the time dependence, so there is a time dependence here. There's a time dependence here, implicit, and there's an explicit time dependence there. So three places where there are time dependent. Take the Taylor expansion there, and I say, if I know the motion of R and P, or time dependent dynamics, that is given by Hamiltonian equations of motion, rest of them I can build by just partial derivative. So I say this is equal to, let's say, df by chain rule now, right? So dr partial derivative, and this is total derivative. R just depends on time, so this is dr by dt plus the partial derivative with respect to p and the chain rule. I've not done anything conceptual. Whatever our knowledge is about partial derivatives, I've just expanded this. But now I notice that, so any function or any quantity that is depending on position and momentum gets a position dependent, or the dynamics of the position and dynamics of the momentum are coming in, which is described by Hamilton equations of motion. So I can put that in there. So I use that in here, and now I'm going away from standard partial derivatives. This is now an information about the dynamics is being used. Like the system has come into picture now. This is about the system. This was any function, but now we're talking about the system. So put that in. And now we're talking about Hamiltonian. This is the partial derivative of the Hamiltonian with respect to momentum. And here it is the partial derivative of the Hamiltonian, which has to do with dynamics with respect to, let's see, oh, this was not, yeah, dp, this is correct, so. And then the negative side. Agreed? So any function or an operator, like when we're doing quantum mechanics, can be written in terms of the Hamiltonian. Now here is where we define something. So this is now we define a quantity. This is where the Poisson bracket comes in. We define the structure F with the Hamiltonian as this is a property decided by F and H, right? A quantity that I was interested in, Hamiltonian, put in curly brackets around it, very similar to commutation relation. R and P derivatives are swapped here, right? R, P. So I say that's R, comma P. This means that first take the derivative with R, then take the derivative with P, swap it. So this symbol here means this whole thing. This is called the Poisson bracket of F with respect to R and P. And since we will be talking about commutation relation, which has very similar symbol, but it will be a square bracket, just to emphasize this is my creation that I put a Poisson bracket there, that P stands for Poisson bracket. So what we have introduced now is F, right? P, F. So F, comma H, Poisson bracket, and R, comma P is equal to the inverse Poisson bracket of F and H with respect to R and P. And we will see that Poisson brackets has some very nice properties. How does the what happens if you swap the operators, what is associativity, and so on, that you will see in the homework, and you will see that there is a one-to-one relation between commutation relation and this. And we'll talk about that, but here, let's try to gather what could this be. So that's as far as the way we have written it, it's just a definition and very straightforward, right? The only thing we did is this is standard for partial derivatives. By replacing this, I made it dynamics. This step introduced the dynamics into the problem. So this is applicable for any function, even a vector, and it doesn't have to be H either here. I can have F and G, for example. So in this way, I have defined it. At this point, it is F and H, but this could be any two quantities, and let's see what it is. For the moment, we will stick to Hamiltonian for a few minutes at least, and then we will move from there. Okay.
What about the other one,
Which other part?
the last one,
Sorry, what? Help me.
the last part minus del F was the.
This is this piece. Oh, I should have written that. Sorry, I never defined it. This is equal to, sorry, I felt I did it, sorry. So I never defined it properly. It's in my head. I said it like this, but it's both pieces too.
In the evaluations at the top, is that P R C H?
Huh?
The evaluations, where it's got R and P on the Poisson bracket,
This one, yeah.
what is the top one?
Oh, this is PB, the short form for Poisson
Oh,
bracket.
that's-
I say that because we have limited number of brackets, right? Brackets and parentheses. You will see that more than one kind of structures satisfy the same properties. Commutation relation will be this F comma H. This is the quantum mechanics commutation relations. I don't have to define this. You already have this. You will notice that cross product, A cross B, that we use all the time, they satisfy the same properties as Poisson bracket and commutation relations. So always have some common features in it, mathematical structure inside it. So when, for example, if I write cross product, now I'm out of bracket, so that's why I put in here Poisson bracket, and here I'll put computational relations whenever it comes in, and here. We don't need the operations R and P, then it's just computation, relations and quantum mechanics, so that's why I write it here.
Just to-
Almost no textbook does that. So it's not necessary, but in this course, just to clarify, probably it's not necessary. Yes, and I was finishing this is the H by D. Oh. Good thing. So any other questions can be done? Oh.
Oh, this time, it's a Poisson bracket, yeah, that means.
This is a Poisson bracket. Oh,
Yeah,
yeah,
last
this
step
is,
is Poisson bracket,
so this whole piece is what is the Poisson bracket?
yeah. We already write that in the previous step.
Yes, so if I were to write this in terms of, so df, any. This is dynamics, notice. Dynamics of an operator. That depends on position and momentum will be given by. The partial derivative to begin with and the Poisson bracket.
In the next step, we just remove that partial derivative, that's why I just asked about that, no.
This is the notation.
No, for the notation, I'm okay.
Uh-huh.
For the Poisson bracket, I'm okay, just for the first partial derivative del f by del t.
Uh-huh. Oh, where is that?
Yeah.
Oh, that is also there. So for example, that's what I said here, that df by dt. If I were to do quantum mechanics, what will I say? If I tell you that I want to find that angular momentum, let's say, what's the time derivative of angular momentum in quantum mechanics? What's the equations of motions for angular momentum? It's a function of time. So it will be,
Well, it'll be angular velocity cross the position.
R plus dp. No, that's the definition, right? R cross dp. No, because R also depends on time, right? You're just expanding this. So this is Heisenberg's equations of motion. If you want, you say L, comma H. That's it. And that is an IH bar now. So this will be I over H bar.
Over.
Yeah.
That's your equations of motion for quantum mechanics. Any operator, you put this in here, that's quantum mechanics. We're not doing quantum mechanics, so here it is Poisson bracket. So it is a no operator F H R T, and I say Poisson. Notice the difference is, of course, turn the, at least notation wise, turn the curly brackets into square brackets, but it's a big leap, very big leap, and H bar. Yes. Oh, I didn't change it. I wanted to change it, but I didn't change it, sorry, yeah, okay. Okay. So this is what you do in quantum mechanics, most of the time, I think at some level, we want to connect with what is already done, what students have already done, and wave equation is something that is very familiar to all the students. And Schrodinger developed a connection between wave mechanics and quantum mechanics. That is very successful, it does great job. But there's another formalism, which is Heisenberg's formalism, very similar. But the main thing is, if you use Heisenberg formalism, all the concepts that you've already studied, you can take it over with some notational changes. Like this makes sense because classical mechanics, we have a lot of understanding of it. So all your old intuitions goes on in quantum mechanics with some additional H bar sitting in there. So there is some addition to it. So it's easy to separate quantum mechanical things and classical mechanics. That doesn't mean that you should not do Schrodinger equation at all. Schrodinger equation has its own advantages. But here, there's this clear distinction between it. Oh, this is what you do and you get quantum mechanics. Why do you do this? That's a bigger question. Like there you bring in all the quantum mechanical reasons, right? I mean, we say that we want to explain this, we want to explain this, and it turns out that just by doing this, you can do that. And Dirac was the first one to realize this connection, and you will see a clear homework example, which is basically Dirac's
Right.
Dirac notation.
Correct.
But he did this jump. This connection between this was first noticed by Dirac, and that observation is relatively easy to follow. And you will do that as a homework problem.
And therefore you develop the direct equations from.
Yes, the Dirac notations are the mathematical tool that you use to develop these things. But at the very heart of it, why the commutation or what's the connection between the two starts from here. And it is not that Dirac first observed this and then did quantum mechanics. It was realized later on. Like I think it shows up in his book, like Dirac's quantum mechanics book. I think arguably the best book written, and it was written in 1931, and it is equally well written and well best, I think, for student even today. So, and this shows up there clearly. And and Dirac was part of the one who started quantum mechanics in a sense, like he did the relativistic quantum mechanics, not the Schrodinger's and Heisenberg's mechanics. But yeah, so so with all that relations, let's try to understand this. And if you see quantum mechanics in some form, like again, most of the quantum mechanics is done in Schrodinger form. Almost everything that I do today and probably next lecture goes through identically into quantum mechanics with all the curly brackets replaced with square brackets, or all the Poisson bracket replaced with. And that's just actually, why should I say just today and next lecture? I'm going to do Kepler problem in the next probably 2-3 weeks. Like there's a lot of things to do in Kepler problem. Whatever way I will do, we won't use Schrodinger equation, we won't do Lagrangian equations or Newtonian equation. We will do Hamiltonian equation. And we will start with Poisson brackets. If you replace that exactly, all the curly with quantum mechanicals, that's the difference between hydrogen atom and the planetary motion. Or maybe I should ask, what is the difference between a hydrogen atom and Earth moving around the sun? Both are 1/r².
Yeah, I've actually kind of thought of that too. They kind of seem similar, just the only difference is the scaling, and due to the scaling,
Yeah.
we can't detect the exact whereabouts of the electron because it's too small, so we use probability to detect its location. But I'm thinking if we could get that to the size of an atom, I mean, it probably would look quite similar to.
So are there Kepler's laws of motion for an electron going around proton?
Use the Coulomb's law with the electric standing force.
Yeah, but it's the same as if you
Yeah.
just replace all the Q's with M's, it is exactly the same. And if you get to Kepler's law, where do you make the distinction ever? We know it because I think with the way we do it, most of the time, most of the textbooks is you start with Schrodinger equation and then you start doing energy eigenvalues immediately. You do energy eigenvalues. And, where does that distinction come? What if I do it this way, or to do it the standard Earth and Sun way, and at the end come up with that? And we will miss something. So that should be highlighted, that if the n equal to 0 state cannot be captured using the standard classical mechanics that we do. That's the quantum piece in there. Or if you do it the classical way, you will get the n equal to 0 term. So, but the ground state of of hydrogen atom is not zero, you cannot really reach the bottom, right? There is some minimal. And that's what is quantum mechanics, in the sense that even though it is accelerating, electron is accelerating, and an accelerated electron does what? Does something special? It radiates. It radiates, right? So if something is going in a circle, it is accelerating. If something is accelerating, it has to radiate. Radiation means you're losing energy. So electron cannot be stable, so it should collapse into hydrogen because it's losing energy. So it should go smaller and smaller radius. So it should collapse into it. But then hydrogen atom is very stable. In fact, its stability seems to be larger than the estimate of age of the universe today. So that's not true. Experimentally, we don't see it. So what is happening? No, it is attractive, right? There is no barrier. It's attractive, so it should, right? It has a centripetal force, or the motion, rather the circular motion that is keeping it stable. So it would like to go and collapse into the hydrogen atom, and if it is radiating, it loses energy, and it should go into it, but it doesn't. So that's how quantum mechanics begins. Like now, that's where Bohr comes in. So how do you explain this? So the explanation is pretty crude, in the sense you say you cannot go down. And you change the whole formalism. So you say that this is a law, that you come in with uncertainty relation or whatever the formalism, but the important piece is that one statement can explain everything. So for example, Newton's law is also something like that. You just throw it at you that, okay, this is what it is. But then one equation can govern everything. So this was started for an electron, explaining why electron doesn't collapse in, but that explains every quantum feature that we know. And these days, the best way of stating it as uncertainty relation, Heisenberg's uncertainty relation. Every system has the corresponding uncertainty relation. And with that, we are able to explain every quantum system that we know of. And in that sense, it is important. But pretty much, it's not that we ever try to explain why electron does not emit using classical principle. That was the earlier motivation, but now we don't do that. Like, you cannot explain why electron does not collapse into it using classical principles. That's the wrong strategy. So we accept that this is the new rule of the system, and that becomes quantum mechanics. That's the spirit in which at least quantum mechanics is done. So you accept a new law, in a sense. Okay. So, but we want to see all that in here, even though we are doing classical mechanics, don't forget that. We are doing classical mechanics, but that connection is almost reachable. Like it's you can touch quantum mechanics from here. It's very reachable. Okay.
Quantum touch.
Yeah. First quantum touch. Yeah. Yeah, nice word. Okay, so
Probabilistic.
probabilistic. Okay, so this is true for any operator. Let's see what things. So how many operators can we think of? Let's do H, R, P. Any other operators you can think of? L, maybe. Maybe. I think those are the operators we have seen. I don't know anything else you can immediately think of. Position, momentum. That's all. Only 4 operators we have seen in the whole course. Okay. Well, we can say it's very efficient. We have managed to study sufficiently with 4 cores. Okay, so let's do dynamics of the Hamiltonian. So you would say H by T plus Poisson bracket H and H. didn't write so much with all this notation. So this is dh by dt. Plus this. And that's clearly zero, right? Unless, like, we don't have any operators, so with respect to R, they compute, and that's equal to, so these two cancel out, and that's dh by dt. So that's the dynamics of, so that if you have a Hamiltonian, even though Rp has time dependence, it's only the explicit time dependence of the Hamiltonian that governs the dynamics of the Hamiltonian. How the Hamiltonian changes with time is completely described by the explicit time dependence. Yes, notice R changes with time, T changes with time, but that doesn't change the Hamiltonian itself. They change in such a way that they cancel out. The dynamics due to R and dynamics due to P, they cancel out always. And only the explicit time dependence governs the time dependence. That's a way to interpret that. Okay. So notice again, there is time dependent, implicit time dependence here, and implicit time dependence here, that's explicit time dependence, like showing it in different arrows. So in principle, there should have been three variations, three possibilities of changes with time, but these two cancel out because of the equations of motion, of position, and momentum. So the dynamics of the Hamiltonian, that means the time derivative, the language is time derivative of the Hamiltonian. You use the word dynamics of the Hamiltonian is governed by only the explicit time dependence in the Hamiltonian, not by any of the implicit. Okay, so that's one trivial statement here, but we had seen this before, right? Remember in Lagrangian mechanics, we proved this in one of your homework. This was a state. Right, so now we see it in slightly different, so everything is consistent as it is. Questions? Okay, so we have R next, so let's try R, right? R by dt, it's applicable for any function, so it should be applicable for R also. R is a very simple function because there is no R dependence in R dependence in R is trivial itself. There is no P dependence in R. There is no time dependence in R, explicit time dependence in R. There is only a total time dependence in R. So you again do, what's the explicit time dependence in R, and R, comma, H, and R, P. So that's the definition. And that's equal. What's the explicit time dependence in R? So that's velocity. So this is velocity, right? What's time, partial derivative of R with respect to time?
Let's.
Yeah, that's correct. That's zero, right? There is R, whenever we say there is only time dependence to begin with, and it's all implicit. So there is no explicit dependence of the position in time. That's the spirit in which we are working. So this is zero. Let's do this. The R by partial derivative of R with respect to R. Now notice, maybe I should, since we have three vectors at this point, right? Let me write this down, but this is very confusing, correct? P minus of dr by dp. Like that's what it means, but now there are too many vectors. So let's just for our sanity, let's say there is I here, that's here, three vectors, and the others we can put a j, right? This is summed up the dot product is between R and P. So I put a J just as a symbol to remind me that, oh, these are the J and J's are dotted. These two are dotted. Is that clear why I wrote the I and J's? There were too many vectors. At this point, I'm confused whether the dot product is with respect to this R or this R. So I'm saying that, oh, this J is dotting with J. So that's it for my own clarity that these two are dotted, these two are dotted. And this is also the index notation. But if you're not familiar with index notation, don't worry about it. We just proceed as it is. Clear? What is the partial derivative of R with respect to R itself? What is this quantity? dr I by drj. Remember what is Ri? Like sort of index. I said I won't use index notation, but this is Ri in the I hat direction, maybe R1, R2 in the j hat direction plus R3 in the k hat, and I is either 1 or 2 or 3. And j is also 1, 2, or 3. So in one of this, I is either 1, 2, 3, or j is either 1, 2, 3. So there are total 9 possibilities there. Right. So the question is, what are those 9 possibilities?
Either. What?
Yeah, or product of delta, very good, right? So if I and j are the same, then it is 1. If I and j are not the same, it is like dy over dx. Then it is partial derivative of y with respect to x is 0. Like we say y is independent of x, right? So that's ij. That's the notation here. So there is this partial derivative of r with respect to r that contributes only when I is equal to j. In dyadic notation, you will just say 1. In dyadic, so this will, if I have to write it as vectors, now these are 2 different vectors, so there are 2 operands, you just say 1, same notation. Okay. So that's equal to 0 plus this 1 dotted with dh by dp, and let's say this is I and a j. So I and a j, I and a j, and this is j. Okay. I at the bottom, right? Because I was. What's the partial derivative of r with p? Think of ri and pj. P is the components of momentum. What's the partial derivative of position with momentum? Remember, in Hamiltonian mechanics, R and P are independent. Like in Lagrangian mechanics, you would say momentum is mass times velocity, at least in most of the systems, and then velocity is derivative of R. But in Hamiltonian, R and P are independent quantities. So it is 0. So independent quantities means it is 0. So this is equal to 0. Right. So this is 0 minus 0 with h by t or j, whatever it is, but it's 0 to begin with. So I don't have to say that's it's a 0 tensor in a sense, but that's just 0. Okay. This is a 1 multiplied with this. There is an I here, so this is equal h by dp. And is that familiar? That's the Hamilton equations of motion, right? So it's consistent. That's nothing new. We have used, like this should be applicable for R also. So it's consistent, right? So this is a trivial statement because we are just practicing with like Poisson bracket, some of the trivial statements we are building up. So that's here dynamics of R with respect to time. Okay. But this emphasized some of the points in here that the dynamical variables, the R and P, they're time independent. Right? And the same thing will work for any of the dynamical variables, R, P, angular momentum, all those are time independent, unless you write it explicit time dependence in there, it is time independent. And that R is itself R, so the partial derivative is 1, and R is independent of P. These are all statements we make in general when we write a Hamiltonian, but those are the details that is showing up here in a more algebraic way, if you want, rather than conceptual ways. Okay. We can do dr. Any questions at this stage? So we can do dr dp by dt, right? That's the third operator we listed there. What will that be equal to? dp by dt plus p comma h r p Poisson brackets. That's equal to, so this is dp by dt plus dp by dr dh by dr minus dp what is this? Let's say, so three of these quantities we have to know. What is this?
0.
0. Momentum is also an independent variable. This one is 0 again. Momentum and position are independent variables. And this one, these three components, there are three components, each one of them is independent with respect to each other. So that's equal to 1. So that's equal to minus h. Here, again, this should be familiar. That's here. What is this equation? Again, Hamilton's second equation with respect to momentum. And finally, yes, Vicky.
No, in the second line, it should be dash by dash P, no, the first.
Oh, here, this one you mean, right?
Yeah.
Yes, correct. So R, P, P, R, yeah, but might. Any other mistakes? Good catch. Okay, so let's do angular momentum. So angular momentum L is equal to R cross P. This is now a compound, like the first three we wrote is almost trivial. Like because Poisson bracket is constructed in terms of H, R, and P, so it is implicit, a lot of things implicit in there. This is one compound structure we can build. And now let's see what is the dynamics of angular momentum. So angular momentum has the same dynamics as the spin. Spin, remember, is angular momentum in the rest frame. So if you are doing spin, you just have to write the same equations there. That's equal to partial derivative of L with respect to time plus L comma H. R doesn't have any explicit time dependence. P doesn't have any explicit time dependence. So L cannot have any explicit time dependence, right? So this is 0. So that's equal to 0. And L is equal to R cross P. So first let me write this explicitly, dL by dr, oh, that's a vector. And again, let me bring in ijk's like this form. Minus dL dp.
So here,
Oh, this again is P, right?
it's here.
L, oh, Li. Oh, what?
That's
This is P, right? P because R and P, right? Denominator is R and P. Minus H by R. Actually, I can even skip the I if you want, because the one that I don't write is approved, is free, the rest of them. Okay, good. Oh, mistake again, BG. Oh, this is G. Good. Okay. We know L, put it in there, so let's see what is this. So D by D R J of R cross P. And so I think we should switch to index notation completely. So let's go back here. What space I think? So let's do the LI over the R J, right? That's what is appearing here. So that's equal to D by drj, and L is R cross P. And we are taking the ith component of it. Is that clear what I mean here in the notation? This is X, Y, Z component, 1, 2, 3 component. This is the first component of the angular momentum. This is the jth component, or this is the ith component of the angular momentum, and the jth component of R. R cross P is written as epsilon I J K R J P K. Is that familiar?
Yes. The VJ.
You guys are familiar, yeah, but I was asking who's the and Pradeep, roughly familiar? Roughly, yeah, that's okay. Yeah. But catch up with that, I mean, they have seen in math method, so that I can demand that they have to know, but you guys are fresh here, so at least in undergraduate somewhere, you've seen it. Pradeep, that's all?
Yeah.
Familiar, yeah, okay. This is not having any position dependence, so this is not there. We argued that this is also independent. P is independent of R, so it's only, it hits only this R, right? So this is equal to epsilon I J K D R. Oh, what did I do? What's the mistake in this? Use the same index notation. J. Yeah, so here there are 3 J's shown. In index notation, if a if an index comes more than twice, there's a mistake. Okay. You cannot repeat the index except until it is summing up. So this was a new I, and I wanted to write it as a sum. I should use new variables. The J I have already used, K I can use actually. So this is I, M, N, M. Oh, what is that? K is already frozen. So M, N. Is that clear? Okay, for Puja and Pradeep, like epsilon I J K and R J P K means summation, right? This is summation over J, summation over K. I can use any variable I want in the sum. I can say this is M going from 1 to 3, K going from 1 to 3, L going from 1 to 3. But I should not use J because J is already there. Right, so I should avoid using J. If I use the J, then it will be confusing. So J is here, J is outside, so it's representing 2 different. That's why I switched over that. So okay, so that's the quantity, and this is independent. So this is I M N T R M R. J, and this is Pn. I don't hit P because if I hit P, I'll get a 0 because it's independent of position. This is anyway does not depend on position momentum, these are numbers. Right, epsilon I j k plays like that. So it only hits this. And that's basically M and J. That's a Kronecker delta. M J E M. With me? Like this was already another information, another mathematical tool that I used. This is the only place where I'm using the physics that we are studying here. That position, a component of a position with respect to another component is independent, so it's Kronecker. And again, now use the property of Kronecker delta and Levi-Civita symbol. Whenever there's a Kronecker delta, you replace M with J. So this is a rule that I, J, N times Pn. So what I'm doing is that, notice what I'm doing, I gobble up my M and replace wherever M was there with J. So that's the prescription if you want in index notation. Okay, good.
Replace M with J.
Replace M with J everywhere or J with M everywhere and gobble up the one that is repeated. M is repeated here, throw it off. I get rid of them and replace wherever M is there with J. Okay, so that's it. So this is what you can replace Li or J with. Okay, so that's equal to that is epsilon I J N, and then there is Pn, and I'm not using the dot anymore, so it is d by dpj times h. This is gradient, right? So let me write this as good. So what is that quantity equal to? Ijn Pn and d by dpj. Any thoughts here? If you have two vectors, A cross B, the ith component is equal to I A M P N. Oh, what am I writing? I M N. Right? That's how cross products work. Okay. Cross product is always given in terms of Levi-Civita symbol. There is a Levi-Civita symbol and two quantities with indices. So what will this be? Cross product, right? And the only thing now is that this one goes with the first index and the second one goes with the second index. Here it is going in the opposite sense.
These minus.
So it's a minus sign. Okay, so this is equal to minus of P crossed with d by dp. Okay. So here I'm going to do the same thing. Notice this is almost the same except that this is P. So here what you will get is I J IJN, let's say, and this will be R J and d by dRn. And I should give a quiz, right? So let's say this, you have to do it as a quiz. Going from here to here, that's a quiz. It's exactly the same as going from here to there, except now instead of the derivative with position, it is P. Instead of R, it is P. So basically change this and you get a negative sign. So, okay. Why is the second term R Why it is Rj not Rn? Epsilon ij. Here? No, this here.
Yeah, epsilon ij.
Because I'm going to see this was hitting here. There it will hit the second one. So that changes the index. You have to explicitly do that. Yeah. I'm looking at the answer and rewriting it in a sense. So this is equal to P cross d by dp minus of r cross, no, plus actually, r cross d by dr of h. And is that familiar?
Minus.
Minus this part. Oh, so that wanting to write it. Okay. Where did you see this before? In your homework, when there was rotational transformation,
Under regime.
under rotations, how does some quantity change? This is the operator that you saw. We are doing how angular momentum changes with time. It seems like for some reason there is a rotational operator that is showing up. It's an indication that angular momentum has to do something with rotation. You will see that more clearly soon. Okay. Well, except for the fact that some index notations were not, you were not fluent in it, but otherwise, overall, what we are doing is give me an operator in terms of R and P. I'll give you the time derivative because I know R and P how it changes. So this is how it is built out. This is how you construct compound structures. You know how R and P changes. If there is a compound structure, this is how you will use to construct that. Right? Before we finish today, so let me quickly say how what we want to do next time is what we have done here is start with a general function if you want, and we have been talking about time derivatives. Only time derivatives, right? This is what we have done. F comma H, Poisson bracket, R comma P. But Poisson bracket is a bigger statement than just time derivative. It's a variational statement. And now let's, instead of writing this, we want to do this as a variation. Same concept, but I'm changing my notation. Instead of telling that I'm going to change with time, I'm going to change my notation to, I'll gobble this up because that whenever I do the time derivative, I'll understand it this way. And this is equal to F times, now it's almost equivalent to multiplying by time. So this is H times dt. And in the time case alone, only with the time, so except for time, let's say. And I did it for time. Now, so this means explicit time dependence. How about that? This symbol means, how do I say this? Here. This is explicit time. Because so that is basically to capture this term in there. So in general, I would like to talk about variation in any quantity, any variable, and what is showing up. For example, translational, let's say translation now. Remember was delta epsilon, right? Or delta R.
Yeah.
Right, that was P delta. And actually, maybe I should say, yeah. Remind, what was this operation? Any idea? Recall this, what was this equal to? G, the generator, right? G. It is written in terms of P and the Hamiltonian. Anytime I need a variation in F equal F and G. So if I want translation, what I do is R is something, time is something. So if I want how an operator changes under translation, I put that appropriate operator there and get the form. We'll do this slowly here. And then F can be anything. I can ask how does momentum changes under translation? How does angular momentum change under translation? Give me any operator here, I'll tell how it changes under a transformation because this is what the transformation quantity is. Here we have done it for time transformation because then delta R is 0 under time. Delta R does not change. We'll do this more carefully and define these things more carefully. Proceed. Okay. Thank you.